Hi guys, this is part 2 for the synchronous counters. In the part 1 we have already discussed the basics of the synchronous counters. So in this video we are just going to see the applications of the synchronous counters, or we can say the extension of the synchronous counters. In the previous video we have saw the synchronous 3-bit up counter. So the circuit diagram is this. And we have also saw the synchronous 3-bit down counter also. So the circuit diagram is this for that. And finally, in the ending of the video, we saw this, that is synchronous 3-bit up down counter. When m is equals to 1, we can perform up counter. When m is equals to 0, we can perform the down counter. But in this video, we are going to learn the BCD counter, means how to design the MOD-10 synchronous counter in this video. And the next thing we are going to learn in this video is the counter. The counting sequence is random. Suppose they have given the 3 means 0, 3, 5, 6, and again the sequence will be continuing up to when the power is off. So we have to design the counter which can perform the counting of this sequence. So in this video only we are going to discuss this concept also. So let's see how to do that. So as we saw in the previous video, we are just going to follow the same steps to obtain any kind of the synchronous counter. The first step is to find the number of flip-flops. So let's see for BCD counter, BCD synchronous counter, how many flip-flops are needed. So if you observe that BCD means what? Total 10 states. So 10 states means we are going starting from 0 to ending at 9. So basically we have 10 states starting from 0 to 9. So as the last one is or the highest one is 9, we can observe the 9 in binary is what? That is 1001. So we can observe that 1001 means what? Total 4 bits. So 1001, 4 bits. So 4 bits means that is 4-bit counter. 4-bit counter means in that we are going to use the 4 flip-flops. So this is one way of finding the number of flip-flops, or you can use the formula to find out the number of flip-flops. So the formula is n, the capital N is equals to 10 here because this is BCD. So capital N is less than equal to 2 power n. So as n is equals to 10, so 10 less than is equals to 2 power n, the n is equals to 4. Means 2 power 4 is 8, right? So we can have that thing that equal to or less than. So we can say we are going to use the 4 flip-flops for the finding of BCD counter. So the next point is draw the state diagram. As we are designing the MOD-10 BCD counter, so 10 states we already discussed the starting from 0 ending at 9. So 0 means what in binary? That is 4 zeros, 0 0 0 0. So 9 means what? That is 1 0 0 1. So for that we need to have all the total 9 states, means the total 10 states from 0 to 9 as representing as a circle. This is known as state diagram. And you can also see the truth table also there, that is Q0, Q1, Q2, Q3 are outputs. For simplicity, we can also represent inside the circle as normal decimal numbers also. The next step is to select the type of flip-flop that we are going to have and draw the excitation table for that. So first of all, if you see, I am going to have the JK flip-flop for MOD-10 counter, MOD-10 BCD counter, and for that I need to know about that excitation table of the JK flip-flop. So this is the excitation table of the JK flip-flop. So we have to have the transition from Qn to Qn plus 1 and corresponding JK inputs. So I hope you know this. The next important thing is that we are going to draw the present state and next state. So how we can get this? So simply present state is nothing but starting from 0 to ending at 9. Total 10 states. So that is the general truth table that we already know. So that next state means if you standing at 0, if what is next state, that is 1. So that is the next state. So all the next state corresponding to the present state that you are going to represent in the truth table format. The whole table is known as the next state truth table. The outputs are indicated with the Q3 plus, Q2 plus, Q1 plus and Q0 plus, meaning that those outputs are next state outputs. So finally, if you stand at 9, that is 1001, then again you are going to come to 0. You can also observe in the next state, that is again 0 final, the last state. And the next step is, first of all, we decided to use the JK flip-flop. So JK flip-flop, each flip-flop has 2 inputs. Like that we are going to use for BCD counter total 4 flip-flops. 4 flip-flops means total we are going to have total 8 inputs. That is J3 K3, J2 K2, J1 K1, J0 K0. So I have left all these columns because we are going to fill all these columns by comparing present state and next state. And by using the K-map, we are going to have the J3 K3 expressions, and we are going to have the final circuit diagram for the MOD-10 counter. And the step is to fill all these columns. So let's see how to fill these columns, and next how to make the K-maps. So the first step is to find J3 K3. For J3 K3, I have took the excitation table of JK in the top right corner. So first we need to compare Q3 plus, because from the present state, how it is changing to the next state, that we have to compare with the excitation table of the JK flip-flop, and we need to place JK in the J3 K3 columns. If you observe first excitation, that is Q3 to Q3 plus, that is 0 to 0. So same Q means 0 to 0, you are going to compare in the top right corner table from the excitation table of JK. So that is 0 to 0 transition is JK corresponding inputs are 0 don't care. So place exactly 0 don't care in the table. As the same way you are going to fill all the transitions from Q3 to Q3 plus 1. You are going to compare with the excitation table of JK flip-flop, and again you are going to fill in the columns of J3 K3 columns. So we have completed the one of the flip-flop inputs, that is J3 K3. For the next flip-flop J2 K2 inputs, so for that we need to have the two columns. So for that two columns we need to compare the Q2 plus 1. So for that we need to have the transitions. So if you observe the first transition, that is 0 to 0, you are going to see the top right corner table, that is JK flip-flop excitation table. So 0 to 0 is 0 don't care, the inputs are JK. So simply place the 0 don't care in the J2 K2 column. Similarly you are going to fill all that column with the help of the JK excitation table in the top right corner and the Q2 plus 1 transition. Similarly for the next flip-flop also, the third flip-flop, that is J1 K1. So for the J1 K1 we need to compare Q1 plus 1 as the same in the top right corner, the excitation table of the JK flip-flop. So if you observe the first one is 0 to 0, again 0 don't care you are going to place in the J1 K1 row. So if you observe the last one also, that is 0 0, again you are going to place in the J1 K1 column, last column as 0 don't care. So similarly you can compare all of them and you can place. I hope you can do that. The next step, if you observe the last flip-flop, inputs are J0 K0. For the inputs J0 K0, for that you need to compare the Q0 plus 1. So if you observe the same excitation table, the first excitation is from 0 to 1. Q0 is changing to Q0 plus 1 as 0 to 1. So you can see in the excitation table in the top right corner from 0 to 1. So that is 1 don't care. So place exactly 1 don't care in the J0 K0 row and exactly compare all of them and fill that J0 K0 columns. So as we are having 4 variables, that is Q3, Q2, Q1, Q0, we are going to have the 4 variable K maps for that. First I need to find out the expressions for J3 and K3. So I have the minimal expression. So in the J3 K3 column we are going to trace out all the min terms. So if you observe the J3, I am going to have min term in the 7th position and don't care conditions in the 8th, 9th position. And why I have highlighted 12, 13, 14, 15, 11, 10 in the red color? Because these are don't care conditions. The next step I am going to fill this with the help of don't care, because these are we don't know. Up to this is BCD counter, right? BCD up counter. So that is the reason we don't know about these conditions. So we are going to fill out this with the help of don't cares. So similarly if you observe the K3, so we have min term in the 9th position and we have the don't care situations in the 0, 1, 2, 3, 4, 5, 6, 7. So fill out all of them. So I said before only that 10, 11, 12, 13, 14 and 15 we don't know about that conditions. So generally we are going to take don't care situations because this is MOD-10 BCD counter. So for the K3 also we are going K3 K map also we are going to have the same, that highlighted in the red box, fill always with the don't cares if you are doing MOD-10 counter. The next step is to group them. So if you observe J3, we can group of 2 elements, that is 7 and 15. It will cover all the ones. So if you observe that we can make group of 1, that is J3 is equals to Q2, Q1, Q0. So similarly if you see the K3, you can cover the 1 that is in the 9th position with the help of group of 8 elements. That becomes a group K3 is equals to Q0. Similarly if you observe, now we are going to find out the second flip-flop inputs, that is J2, K2. In this also we are going to follow the K map method only. So first with the help of K map I am going to find J2. So similarly place the min terms in the position 3 and don't care in the 4, 5, 6, 7. So for the K2 also place min term in the 7 and the remaining don't care situations fill according to that. According to the truth table you can see over there, you can compare and fill that. And one more important thing, don't forget to fill 12, 13, 14, 15 as don't cares, because that helps our grouping much more easier. Because we can make largest groups with the help of that. If you forgot, we cannot have the minimal expression. So if you observe the J2, that is Q1, Q0, because we can make group of 4 elements 3, 7, 15, 11, and we can suppose if you see the K2, that is also the same row, that is same column, that is 3, 7, 15, 11, but the one position, the min term positions are different. But if you see the expressions are same for J2, K2. So we can have that J2 is equals to K2 expression for the thing, for the second flip-flop. Inputs are same for second flip-flop. And the third flip-flop we will observe, that is inputs are J1, K1. Similarly, we are going to place all the minterms in the K maps. If we observe, we have minterms for the J1 as 1, 5 and don't cares are 2, 3, 6, 7. And fill the remaining things with the don't cares. The remaining thing means I mean the 12, 13, 14, 15. Including 11. So because 10, 11. So for the K1 also place exactly the minterms, all the minterms in that and remaining as don't cares. Highlighted in the red color. If you group them, you can also observe that 1, 3, 5, 7 made as a group. That is J1 is equals to Q3 bar Q0 can be made as an expression. So for the K1 expression, you are going to make group of 8 elements. That is, we can have the simple expression K1 is equals to Q0. So for the third flip-flop, inputs also completed. The expression we got. Finally, for the fourth flip-flop, if you observe the inputs, that is J0, K0, can be easily obtained because all the terms are just ones and don't care. So instead of having the K map, we can simply say that J0 and K0 are 1 because all are 1 and don't cares. So you can also observe that we have all the expressions. That is J0, K0 we have, J1, K1 we had, J2, K2 also we find out with the help of K map. So J3, K3 also we find out first itself. So with the help of these 4 expressions, means all the 4 flip-flop inputs, total 8 inputs, we can have the final circuit diagram for the MOD-10 BCD Synchronous up counter. Basically it will count from 0 to 9, total 10 states. So if you observe J0, K0 expressions, both are equal and equal to 1. So connected to 1. So if you observe J1, K1, so J1 is equals to Q3 bar Q0. For that, so in between we have AND gate. So I took Q3 bar from the last flip-flop and attach it to the AND gate. So simply I took another input, that is Q0, and attach it to the J1. And for the K1, simply take Q0. So you can see this is all the flip-flops are synchronized with the clock at a time. So that is why it is known as synchronous counter. And MOD-10 BCD, because of we are having logic here with the help of K map and that logic. If you see the second flip-flop, that is J2, K2 as inputs, so that is Q1, Q0 as inputs. So simply take a AND gate for that and have the inputs Q1 and Q0. And for the last flip-flop, the inputs the J3 as Q2 into Q1 into Q0. So simply attach the first input with the previous input, means previous output of AND gate, and second input is Q2 attached with the J3. So simply for K3 attach Q0. So simply like with the expressions we can build the circuit. After building the circuit, it's not done yet because we need to check for the lockout condition. So while counting, if count goes wrong, what it should select? So it is known as self-correct. So it should correct self itself. So that is known as if we are going to check for the lockout condition. So let's see how to do that. So as we are using the MOD-10 counter, basically starting from 0 and ending at 9. If you observe the 10th position, again it has to return to 0. By chance, if it reaches to 12th position or 15th position or 13th position, by chance, this is the counter, right? Anything might be possible. So by chance, if it reaches that position, it has to self-correct and again it has to enter the same state diagram. Otherwise, it might be stuck in that position only. So that is known as the lockout condition. So we need to check out for that lockout conditions and we need to check out the circuit diagram also once. So what is self-correcting? So now we will going to have the explanation for that. See clearly, now we are going to obtain for remaining states also the state diagram. So for that state diagram we need to have the present state and next state. So if you see in the present state, I have took from 10 to 15 the remaining states. So we will be going to find out the next state expressions, that is Q3 plus, Q2 plus, Q1 plus, Q0 plus with the help of the present state and the expressions that already we had. So correspondingly I have took the remaining inputs, that is J3 K3, J2 K2, J1 K1, J0 K0. So we are going to find out all these 8 inputs with the help of the expressions that we have already got. I will explain one thing like that you can fill the remaining things. So if you observe how we are going to fill out these inputs, that is J3 K3 like that. So if you observe the J3 K3, the first one, that is I filled with 0 0. So how I filled with 0 0. So if you observe the 10th position 10. So as we are filling J3 K3, we are going to have the J3 K3 expressions. The J3 expression is Q2 into Q1 into Q0, K3 is Q0 simply. First observe that 10 column means 10 row, that is 1 0 1 0. Q3 is 1, Q2 is 0, Q1 is 1, Q0 is 0. So exactly for J3, so 0 into 1 into 0, you can place that Q2, Q1, Q0 in the expression. For the K3 simply as 0, that is Q0 simply as it is. So now you got how we are getting 0 0 because J3 is 0, K3 is also 0. So for the 11, if you observe the 11, I filled with 0 1 correspondingly J3 K3. How I got that 0 1? Because if you observe that 11 row, that is fill exactly the J3 K3, fill that. So Q2 is what? 0. Q1 is what? 1. Q0 is also 1. So fill that is 0 into 1 into 1. So that gives J3 as 0. So K3 simply 1 because that is Q0. So I hope you can fill out that remaining things as well as comparison. I have same that. So if you want J0 K0, simply compare the Q0. Sorry, the row wise. If you want the 10 row, you are going to compare the J0 K0 like that you are going to see. So I hope you can do the remaining values. If you done that, please check out or cross check these values. So these are the values that I am giving here. If you observe J0 K0, there is nothing to put in J0 K0 expressions because J0 K0 equal to 1. So we are going to have the J0 K0 expressions as 1 1 only always. Yes, now very important step begins. Now let's find out the next state. For the next state that we are going to compare the J3 K3 and Q3. This is very important point. Remember that. How we are going to compare? So just remember the truth table of the JK flip flop. For the Q3 plus, you can see that I have highlighted in the blue color that one itself. Means how we got that one? We are going to see that J3 K3 is equals to 0 0. If you observe, if you see that JK flip flop or if you remember the JK flip flop truth table, when you have the JK as 0 0, what is the output? That basically hold condition. Hold means what? Whatever may be the previous condition will be reflected to the next state. So previous condition Q3 we are having 1. So for the Q3 plus also we are going to have the hold condition, right? So hold means what? The same thing, 1. So similarly if you observe J3 K3, the next one that is as 0 1. So if you observe again, if you all remember or recall the JK flip flop truth table, if you have J3 or JK as 0 1, we are going to have our flip flop means the present state reset. So as the Q3 is 1, we are going to reset, that is the next state is Q3 plus is 0. So likewise you can fill all that Q3 column, Q3 plus column. Similarly if you want Q2 plus column, we are going to compare J2 K2 and Q2. So likewise if you want the Q1 plus 1 column, you are going to compare J1 K1 and Q1. Like that you are going to fill out all the next state columns. So the main thing that we are building for the remaining, or we don't care that is from 10 to 15. For that, why we find at the next state conditions? Because if you stuck in the next state, we are checking, we are able to get out in the original states or not. So if you observe the present state is 10, suppose that is 1010. The next state is that is 1011. That is basically in decimal, that is 11. So if you are in the present state as 11, the next is 01000, that is 4. So likewise you can compare in the state diagram also. I have simply represented in the state diagram. So likewise if you stuck in any of the position that you want, you can compare in the state diagram for simplicity. For example, if you stuck in the position of 15, that is last position, that is 1111. So the next state is 0000, that we have obtained in the next state. So in the state diagram also I have represented that if you stuck in the 15, in the next state you are going to come to 0. So wherever may be the invalid position that you are stuck, again it will come to the original state table. So that is known as self-correcting counters. The same sentence written over there. So counter is known as self-correcting because if counter is in the one of the unused state means the remaining things except up to 9 we are going to see. Remaining 10, 11, 12, 13, 14, 15 are unused states, and it comes back to the valid state after one or more clock cycles. Then it is known as self-correcting counter. So basically BCD counter is known as the self-correcting counter. If it is self-correcting counter, no need to change the circuit. If not, we should change the circuit diagram also. If you observe in the BCD synchronous counter, we have formulated or we have created the circuit diagram for that. And we also understood the state diagram in the unused states also. So this is the self-correcting counter. So there is no need to modify the circuit or the diagram. If we had the non-self-correcting counter, then we need to modify our circuit diagram. In the general up counter or down counter, we cannot have our non-self-correcting counters. So always we are going to have the self-correcting counters for the normal binary sequence. For the random sequence, suppose in the examination they might ask, suppose find out 0, 3, 5, 6. So this is the random sequence that you need to generate with the help of counter. So then that kind of situations we need to have, or we need to modify our circuit diagram, because those kind of circuit diagrams or might not be self-correcting counters. So that also we are going to see in this example or in this video only. So in this video we are going to design the synchronous counter, that is counter with counting sequence 0356, and again it repeats the sequence, that is 0356 again, 0356 again, like that it continues. I took some random sequence, so with the help of this example you can have your own examples and you can try it out by your own. So as it is, the first point is to find the number of flip-flops to be used. So if you observe, that is we have the sequence of 4 count, that is counter as 0356 0356. So highest number is 6. So 6 in binary is 110. So 110 means we are going to store the binary digits as 110. So as we are requiring the 3-bit, so we can say this requires 3-bit counter. So 3-bit counter means we are going to use 3 flip-flops. Or for this random sequence generator or random sequence counting, we have another formula. So formula is n, capital N greater than equal to 2 power n minus 1. So and as n max is 6, we can simply put 6 and we can find out our n is equals to 3. So we decided number of flip-flops. In the same way, the next step is to draw the state diagram. So the sequence is 0356 0356. So you can see over there I have starting with the 0, 3, 5, 6 and again going to 0. So these are the 4 means the remaining 4 states, that is unused states or the remaining states, or I can simply say invalid states for this sequence. So you can see in the truth table also, that is Q2, Q1, Q0. The first 4 states are used are valid states and the remaining 4 states are invalid states, highlighted in the yellow color. And the third step is to select the type of flip-flop that you are going to design. So I am going to use the T flip-flop for this random sequence. So you can use JK flip-flop also, that is your wish. So if you are using JK flip-flop, you are going to have the 6 inputs, that is J3, K3, means like that you are going to have some 6 inputs. You can have your labeling your wish. So as we are using T flip-flop, we are going to have just 3 inputs. That is the reason I am going to use the T flip-flop. And for the T flip-flop, already I hope you know aware of T flip-flop excitation table. So this is the excitation table of T flip-flop. So as we decided to use the T flip-flop, in the T flip-flop we have each and every flip-flop has one input, that is T input. So that is the reason I have took an individual thing, like not like JK. So here we have 3 inputs, T2, T1, T0. So we are going to fill all these means these T inputs with the help of the excitation table of the T flip-flop as shown in the top right corner. As we saw similar in the JK flip-flop, the same thing that we are going to follow. We are going to compare Q2, Q2 plus 1, and we are going to see the excitation table of T flip-flop and we are going to fill the T2, T1, T0. So I hope you can fill that the T2, T1, T0 by seeing the excitation table in the top right corner. So this is the, after filling that you can have a look over this. Now we are going to obtain the T2 expression for the first flip-flop, the T2. We are going to obtain the T2 input with the help of K-map. So as we are having only 3 variables, that is Q2, Q1, Q0, we are going to have a 3 variable K-map. So but remember one thing, this is not the normal counter. So this is the random sequence counter. So you can see over there, we have random sequence. We have started with M0, then M3 came, not M1. So M5, M6, this is our sequence. The highlighted one, that orange highlighted one or yellow highlighted one is not considered. Those are unused states. So unused state means what? So those are don't care situations we are going to take in the T2 or while making the K-map as a group. So you can also observe there we have T2 expression in the minterms 3, 6 and don't care situations in the 1, 2, 4, 7. Because those are not specified in the sequence, so that we are going to have the don't care situations. So after grouping we can group 4 elements, that T2 is equals to Q1 output. So for the next flip-flop, the input is T1. Now we are going to find the T1 expression with the help of K-map. So as this is also 3 variable, we are going to have the 3 variable K-map. So without K-map also we can judge that T1 is equals to 1 because all the inputs are don't cares and ones. So ultimately we are going to group all the elements. So T1 is equals to 1. The last flip-flop, the input is T0. For the T0, if you consider except 2 terms, all the terms having whether don't care or 1. So if you place all the terms in the min terms in that and we are going to have a grouping that. So group 4 elements can be made, that is 0, 1, 4, 5. So T0 would be Q1 bar. Finally, we have all three inputs for three flip-flops. That is T0 is equals to Q1 bar, T1 is equals to 1, T2 is equals to Q1. So based on inputs we had, so take three flip-flops. So as this is the synchronous circuit, we are going to have the clock pulse at a time. We are going to pass clock pulse. So if you observe the T0, the expression is Q1 bar. So simply we had Q1 bar in the second flip-flop, take it as input. I can just take it as a feedback. So T1 is equals to 1 for the second flip-flop, take directly 1. So for the third flip-flop T2, the input is Q1. So we had Q1 as previous output, take that directly. So this is the thing. So a random sequence circuit that they have given, we have built a circuit using synchronous circuit counter. So it's not done yet. I said before only. A not self-correcting example I will take and I will show I said. So this is the thing. Now we are going to check for lookout condition. This will not satisfy and we are going to modify the circuit. So let's see how to do that. So before that, first of all, we need to understand how we can have the next state for the remaining things. First of all, we need to draw the state diagram for the remaining things. And we are going to merge with that and we are going to check it is merging or not. Means other than that sequence, suppose if the counter goes into the invalid states or unused states, suppose example if it goes into the fourth state, unfortunately, some by manual error, then it has to come back to any of the one of the state, that is 0, 3, 5, 6. Otherwise, we are going to change our circuit model. So for that, we already saw the discussion in the JK flip-flop. Let us have a thing over here. So first of all, we need to fill the T2, T1, T0 for the unused states, that is 1, 2, 4, 7. For that, you are going to place, suppose in the previous thing we already saw. Suppose if you want the forced minterm, that is 0, 0, 1. So we are going to have that T1 is equals to Q1. We have already got the expressions. So simply T2 is equals to 0. So if you can also observe that the T2 present inputs for the first one, T2 is 0. The next one is 1. How we are getting 1? So that is M2. M2 is equals to Q1, T2. So simply like that, we are going to fill all the present inputs. So then the next step is to find the next state of this. So how we can find the next state? So simply we are going to recall our truth table of the T flip-flop. If T is 0, the output or the present state will not toggle. If T is equals to 1 only, the present state will be toggled to other state. So I hope you can understand. In the present state, if you observe in the T2 column, so you are going to see the first as 0. So the Q2 is 0, so it will not miss. T2 is 0, as T2 is 0, the Q2 will not be toggled. That is in the Q2 plus also, that is 0. So if you observe in the T2 as 1, so Q2 is 0. It will be toggled to Q2 plus 1 as 1. So like that you can compare and you can have a look over that. So like that fill all that. So after the finding the next state, that we are going to draw the state diagram for that, so that we can clarify that it is not a self-correcting counter. So if you observe, just these are unused state, present state and next state. So if you see, if you enter the unused state, whether it will be redirected to the used state or not, that we are going to check. So if you observe, we are in the position 1, it will again retraced or pass it to 2. So you can also observe in the diagram. Suppose if you are in the position 2, it will going to 4. So if you are in the position 4, you are going to position 7. If you are position 7, you are going to 1. So like that the circle continues, but there is no link between these two circuits, or these two counters, or used states, unused states. There should be some connection, so that is the reason that we are going to modify the circuit. Suppose instead of having this, so if you have 0356, 0356, so instead of having that, if number or counter enter some other, suppose 7, so we might face some errors. So that is the reason we are going to modify now. So let's see how to do that. First of all, let's see the definition. So counter is not self-correcting. We already know that. So generate the reset pulse when the counter goes into invalid state. So we are going to generate the reset pulse and we are going to send, so that we are not going to obtain, or we are not going to have the invalid states. So the reset input should bring the counter one of the valid state. So here valid state is 0, 0, 0. So if you want reset some other thing, suppose if you have the reset is 1, 1, 1, you are going to reset to 1, 1, 1. Like that you are going to reset. For that reset, we are going to connect it to clear. So first of all, we need to obtain the reset expression. So for that, I need to take the invalid states. The invalid states are not present in the sequence are 1, 2, 4, 7. So for that only reset is 1. So for that we need to clear when that state appears. So place all of ones in the K map. So we can simply say that this is the half adder format. If any of the thing, full adder format. If any of the thing is this cross cross shaped, we cannot group them. So we can say that is Q2 XOR Q1 XOR Q0. You have to remember that. So 1 4 7 2, this can be have, if you have remember the full adder, half adder, these kind of things. So this is a similar thing, that kind of. So we have obtained the output expression R is equals to Q2 XOR Q1 XOR Q0. So simply the circuit would be the same. Just the extra thing that we are going to add as 2 XOR gates, or simply one XOR gate with 3 inputs. So that gives our XOR operation, Q2 XOR Q1 XOR Q0. So the XOR operation should be applied to clear to all flip-flops at a time. This is the circuit diagram after eliminating the lockout condition. So you can see all the things or remaining things, the invalid states are pointing to 0 or a valid state. If the counter enters the invalid state also, again it has capability to enter to valid state. So that is the reason we are going to modify the circuit for this kind of the eliminating the lockout conditions. I hope you understood this video. Thanks for watching up to now.